press the bell icon on the YouTube app and never miss another update.
Now we are discussing first PUC physics chapter oscillation. We have started earlier, and in the previous class we have discussed how to express simple harmonic motion in terms of a particle executing uniform circular motion, So when the particle completes one circular motion, the foot of the perpendicular completes one to and fro motion about any diameter of the circular path. So the period of circular path is equal to period of the to and fro motion of the foot of the perpendicular, which represents a simple harmonic motion, and frequency of circular motion is equal to that frequency of simple harmonic motion. And using this concept, we have derived equation of simple harmonic motion, Equation of simple harmonic motion gives displacement y of a particle executing simple harmonic motion at any instant of time t in terms of two constants of simple harmonic motion, a amplitude of simple harmonic motion and omega angular velocity of simple harmonic motion. This equation involves both linear term y and a as well as angular term omega, that is, we have y is equal to a sin omega t or y is equal to a cos omega t, that we have derived that one, Now for an instant, let us see here. Here I have a simple pendulum, a bob. This is point of suspension. Now the length of the simple pendulum is equal to the distance between the point of suspension and the center of gravity of the bob, and you see that this is the equilibrium position of the bob. Bob is at rest. Now to make it execute oscillation, we have to be pulled aside, by applying an external force to change its position of equilibrium. When we leave this one, this executes a simple harmonic motion. The period of oscillation depends upon the length. If we increase the length, now the period of oscillation also increases here. Now if I take this amplitude here, now this is the amplitude, maximum displacement. If I increase the initial displacement, then obviously the amplitude of oscillation also increases. Here we can able to see this one, Now can you able to observe the oscillation of that pendulum, that is the bob? So you can clearly observe that it is having a to and fro motion because its frequency is very, very small, Now we have a spring, When it is loaded with some object, now this is called as loaded spring, and when it is set into oscillation, it began to oscillate, If the weight is more, then the period is also more, This is again, we can able to see the oscillation of this loaded spring. And we take another case here, just to understand the difference between oscillation and vibration. Here this is a tuning fork, right? It is a hitting pad. When I hit this tuning fork against the pad, you can able to hear the sound. It began to vibrate. These two are called as prongs, right? And both the prongs execute simple harmonic motion, but we cannot able to identify the motion. I cannot able to see the motion. It is because its frequency is very high. It is about right 512 hertz, right? Now we say that vibration of tuning fork because frequency is high, oscillation of simple pendulum because frequency is less. That is the only difference between when we say oscillation and vibration. The remaining thing are the same. Both are simple harmonic motions, and they exhibit all the characteristics of simple harmonic motion, right? Now, while coming back to our discussion, right, now we will take graphical representation of simple harmonic motion. Right. A graph plotted, right, with the displacement of a particle executing simple harmonic motion versus time taken is called a displacement time graph or displacement time curve, right. A graph of displacement of simple harmonic motion versus, right, time taken is called, right, displacement time graph or displacement time curve, right. So far we have discussed graphs in earlier chapters, that is displacement time graph in motion along a straight line, right, velocity time graph, acceleration time graph, force displacement graph, right, pressure and volume of pressure and volume graph in case of a gas undergoing thermodynamic change, right. Now this graph is called displacement time graph or displacement time curve. Now how to obtain the displacement time curve? Now let us consider a particle executing simple harmonic motion with the center O. This is diameter. Now the particle at position B at time t is equal to 0. Now this can be represented, right, the motion by a graph, right, in which displacement y, displacement is taken along positive x-axis and time is taken along right positive x-axis. Time is displacement is taken along y-axis, time is taken along x-axis. We will take that initial point, right, O, right, that is B, right. Now when the particle executes, right, circular motion with theta is equal to omega t, where omega t is the angular velocity. Now the particle will have the displacement y. The foot of the perpendicular, right, displaces from O to Q as the particle moves from B to P. Now that means as time passes, displacement increases. I can represent like this, right? This is any displacement at time t, right? This represents y at any instant of time t. Now as the particle moves to position C, now the graph rises and reaches a maximum value, right? This maximum value is taken as plus A, because A is the radius of the circular path and the distance OC is equal to radius of the circular path, that is the maximum displacement. When the particle moves to position D, right, now the simple harmonic motion, right, starts moving from C to O with passage of time. Here displacement decreases with the time. So it can be represented like that. It can be represented like that. Now this is the position C. This is the position D. Now the simple harmonic motion has completed half oscillation, right, or half vibration, right, in positive direction, that is above the mean position O. When the particle moves from position D to position E, now the oscillation is moving from O to E, that is in a downward direction of right O. Obviously, when we take from a reference point upward direction as positive, then obviously from that point the downward direction is right negative. So if we take it as y-axis, then OY represents positive y, OY dash represents negative y. Therefore, right, we will have the graph moves like this, right. This is the point E. Now the oscillation has reached the maximum displacement position in a negative direction, right. This represents that by minus A, that is a maximum displacement or amplitude in the negative direction. As the particle moves from right E to B, right. So this is initial position B. I will take it as F for the sake of convenience, right. It has reached the position B. When it reaches the position B, right, we will obtain the curve EB or EF, right. Then when the particle completes one circular motion, the foot of the perpendicular completes one oscillation, and the displacement against time is represented by the curve BCDF, right. Or with respect to this one, right? That is simple harmonic motion. We have O, C, D, B, right? Or here with respect to that one. So for that matter, I can take this as a F. F means O again here. In graph, I have taken F, right? So this curve O, C, D, E, B or O, C, D, E, F represents a displacement time curve, and it is called displacement time graph. The graph is called displacement time graph. Now here, when we observe the graph, this is displacement y at the time t. As the time passes, displacement also changes, and this is graphical representation of that simple harmonic motion. Now we say at time t is equal to 0, right? We have this equation. We have that equation y is equal to a sine 2 pi by t into t in terms of time period, right? At mean position, time t is equal to 0. Then we have y is equal to a sine, right? 0, that is equal to 0. That is, at this point, displacement y is equal to 0. When time t is equal to t by 4, it has reached this position. Now y is equal to, a sine 2 pi by t into t by 4, right? Now that implies y is equal to a, t get cancelled, sine pi by 2, right? Sine pi by 2 is equal to plus 1, y is equal to plus a. That is, at this position, the time taken t is equal to t by 4, and the angle covered is pi by 2. See here, the angle covered is pi by 2. Right. Now when time t is equal to t by 2, it has completed half oscillation, y is equal to a sine, right? 2 pi by t into t by 2, that y is equal to a sine t get cancelled, 2 get cancelled, pi is equal to 0, right? Again you see, the displacement reaches maximum value at C, and again this comes to the mean position after completing half oscillation. Therefore here at D, the time taken t is equal to t by 2, and see what is the angle covered here, right? It has covered, right, 180 degree, that is pi. So with uniform circular motion, the angle BOC is equal to 90 degree. The angle BOD is equal to 180 degree, that is pi. When time t is equal to 3t by 4, right, then y is equal to a sine 2 pi by t into 3t by 4, that is equal to a sin tt get cancel, that is 3 pi by 2. That means 3 pi by 2 is equal to 270 degree. Right, now we have sin 270 degree is equal to minus 1, that is equal to minus a, that is this position, right. So here the time taken t is equal to 3t by 4 and the angle covered is 3 pi by 2. It is the angle covered. Is it clear? Now when time t is equal to t, it has completed one simple harmonic motion. Now y is equal to a sin 2 pi by t into t. Tt get cancelled. Y is equal to a sin 2 pi, that is sin 360 degree, that is equal to 0. So at position F, the time taken t is equal to t and the angle covered is 2 pi. So here the C, when we take y is equal to a sin omega t, that is 2 pi by t into small t, right. So this omega t is equal to 0 here, pi by 2 here, pi here, 3 pi by 2 here, and here this is equal to 2 pi, right. Now this is how when the time passes, at time t is equal to 0, it occupies the position B. At time t is equal to 0, it occupies the position C, right. I mean at time t is equal to t by 4. At time t is equal to t by 2, it occupies position D, completing half oscillation. At time t is equal to 3t by 4, it is 3 pi by 2, right. Now and time t is equal to t, that is equal to period, then it comes to the mean position after completing one right oscillation or one simple harmonic motion, right. Friends, if we write that time period, displacement and angle we can take. Here I take time taken, right. So angle covered, this angle covered is both in, you take radian degree. Now displacement, this is y, this is theta is equal to omega t, this is t. Now when time t is equal to t by 0, right here at angle is 0, theta is equal to omega t is equal to 0, in degree it is also 0, the displacement y is equal to 0. Now at C, when T is equal to T by 4, here the angle covered is pi by 2 in radian, or it is 90 degree, and see the displacement, it is plus E. Now when time T is equal to T by 2, there is position D. The angle covered in radian is pi, in degree is 180 degree, and again the displacement is 0. Now when time T is equal to 3T by 4, here the angle covered is 3 pi by 2, that is 270 degree. Displacement is minus A. And when time T is equal to T, the angle covered is 2 pi, right? Now this is 360 degree, and this is again 0, right? And this completes. This is the changes for one oscillation or one vibration. As time passes, the angle covered may be 3 pi, 4 pi, 5 pi, etc. And the time taken is more than time period, right? That is 3t by 2, 2t, right? 5t by 2, etc. And this is for one oscillation, right? And again, right, this shows the graphical representation, and you know that how we have obtained this equation by substituting the value of t in equation y is equal to a sin omega t. So now I will retain this diagram here, and I am going to take another important concept in oscillation, that is phase, represented by the symbol phi, right? Now we know that we have state of motion of a body, right? Now state of motion of a body, right, can be found using equations of motion. What do you mean by, right, state of motion of a body? What is the displacement of a particle moving along a straight line at any instant of time t? That is given by S is equal to ut plus half at square. Now the state of rotation, right? When a body is rotating, that state of rotation represents the angular displacement of the body at any instant of time t. That is theta is equal to, right, omega naught t plus half alpha t square, where omega naught is initial angular velocity, here u is linear angular velocity, a is linear acceleration for translational motion, and alpha is acceleration for this motion, right, mean angular acceleration for rotational motion. Now here in oscillation or vibration, we have a sin omega t, right? Now when a particle is oscillating, right, we use the word state of vibration or state of oscillation. Here instead of oscillation we are using state of vibration. Now clearly understand the phase of a vibrating particle at any instant of time is called phase, or phase of a vibrating particle at any instant of time is the state of vibration of the particle at that instant of time. That is right. The phase of a vibrating particle at any instant of time is the state of vibration of the particle at that instant of time, right? Now, then what is this state of vibration or phase? The state of vibration or phase of a particle at any instant of time describes position and direction of motion of the particle at that instant of time. Right. Now, the phase of a particle or state of vibration at any instant of time is time describes both position and direction of motion of the particle at that instant of time, at that instant of time. For example, when we take a particle executing simple harmonic motion, there is a simple pendulum. This is the position O. That is mean position when time t is equal to 0. Now, when it oscillates between 2 points. Say M and N. This is one extreme position. This is the other extreme position. Now, here at this point of time, when the particle is moving from O to C, now it is moving here, right? At any instant of time t1, the particle has a displacement y1. Now, as it moves to N and while returning back to O in positive direction, you see, again the particle reaches, right, the same point P, right, after time t2 while coming back. Now it has a displacement y1, the same displacement. Now you see here, if a particle is moving along a straight line, it occupies a position at any instant of time. right? A particle moving along a straight line does not occupy the same position at two different instants of time. But here, at two different instants of time, T1 and T2, the displacement is same, right? So, the position is Y1 here, right? Now, what is the difference between when I take a position at time T1, position at time T2? Both are the same position of the particle from the mean position, but at two different instants of time. So, to locate whether the particle is at P while moving towards right N, or particle is at P while moving towards right. So, during the two directions, right, one is ON, away from the mean position. The second one is NO, towards the mean position. It occupies the same position, has the same displacement, right? Now, in order to decide whether the position P is occupied, right, during motion along ON or motion along ON, we need to describe the direction of motion, in which direction it is moving, right? Now, when we are having the particle position at P, that is at time T1, right, that is the direction is ON. So, here that phase describes position of the particle, at the same time, right, the direction of motion of the particle, right. So, here the state of right position and direction, right, at T1, right, position and direction at T2. Position is same, but the direction is different, right. So, that to avoid this confusion, right, when to decide clearly whether the position P is occupied during motion away from the mean position or during motion towards the mean position, we need to indicate both position and direction of motion at that instant of time, right. This quantity, physical quantity that gives both position and direction of motion of a vibrating particle at any instant of time is called phase, right. So, phase or state of vibration of a particle at any instant of time t, right, gives the position and the direction of motion of the particle at that instant of time. Say here again, while moving from O to M, it occupies a position P dash, again having the displacement y1 here, right. Now, here it has taken time t3. Now, it is moving to M, and while coming back, right, it reaches the same position at t4. Now, at t1, t2, t3, t4, that is displacement is same. Why? But the direction of motion are different. Here we have 4 directions. ON moving away from the mean position in positive direction. NO moving towards the mean position in positive direction. OM moving away from the mean position in negative direction. So, MO moving towards the mean position in negative direction. So, in oscillation or simple harmonic motion or vibration, the particle has 4 directions of motion, right. When we are locating the particle, that means finding the distance of the particle from the mean position, it is also important to know what is the direction, because it can have the same position, I mean same displacement at 4 different instants of time, right. Here the position is y1 during away from the mean position. Position at t2, right, is the particle moving towards the mean position in positive side, right. So this is negative side. Okay. So here this at time t1, t2, t3, t4, here according to that figure and our discussion, position is same, but the direction of motion are different. Therefore, the state of vibration of the particle is different at 4 instant of time. So, there is a phase phi 1 at time t1, there is a phase phi 2 at time t2, there is a phase phi 3 at time t3, and there is a phase phi 4 at t4. What is it phi 1 represents? That represents position of the particle and direction of motion at t1. What is t3 represents? Again position of the particle as well as direction of motion at time t3, and that quantity is called as phase, right. Now, how to measure phase, right, or state of vibration, right. Now, the phase or state of vibration of a particle is expressed in terms of fraction of time period t, or fraction of angle, right, 2 pi, right, that has right elapsed, right, since the particle has crossed its mean position in positive direction. I will write it on the board. Right. Now, the phase of a vibrating particle at any instant of time is measured or defined as the fraction of time period or fraction of angle 2 pi that elapsed since the particle has, right, crossed its mean position in positive direction, right. Now, when the particle is at O, right, when the time t is equal to 0, right, now no time has elapsed, right, and the phase of the particle is said to be 0. So, now I will take it as O here, right. So, the position is represented by O, right, the C D, E, F point. Now at O, right, time t is equal to 0 and we say phase phi is equal to 0. Right. Now at C or M here. Now the time taken is equal to t by 4. Therefore, phi is equal to t by 4 or that is equal to pi by 2. Right. So, phase of the particle at C, right, is, right, t by 4 or pi by 2. You see, what is that t by 4? It is the fraction of time period that has elapsed since the particle crosses its mean position in positive direction, right? So, the phase at C is the fraction of time period taken by the particle since it last crosses its mean position in positive direction. We say phase at T is, C is t by 4 or pi by 2. So, at T, that phase phi is equal to t by 2 or pi. The phase at this point D is t by 2 or pi because when particle is at position D after completing one half oscillation, right, now again its displacement is 0, right, but it has completed one vibration. Here also displacement 0, but here also displacement 0. Here time t is equal to 0 represents O. Time t is equal to t by 4 represents particle is at M. And when we say that phase is t by 2, the particle, right, has reached the mean position after completing one half oscillation. Now at E, the phase is 3 t by 4 or 3 pi by 2. It is the phase at this point. Now at F, now the phase phi is equal to t or it is equal to 2 pi. When I say that the phase of a particle is 0, the particle is at mean position before starting the oscillation. When I say that the phase of a particle is t by 4 or pi by 2, then the particle has reached its maximum displacement or extreme position in positive direction. When we say the phase is t by 2 or pi, the particle is at mean position after completing one half oscillation or vibration. When the phase is 3t by 4 or 3 pi by 2, then the particle is in extreme position in negative direction. When I say that phase of a particle is t, capital T or 2 pi, that means the particle is again at mean position, right, but it has completed one oscillation. See here, at O, at D, at F, right, the particle is at mean position only, right, but the direction of motion in the next instant is, right, different. When I say phase is 0, now it starts moving away from the mean position in positive direction. When particle is at B, right, it is at mean position, but it starts moving away from the mean position in a negative direction. Now when particle is at O, it has completed one oscillation, right, and then starts to move in positive direction away from the mean position. Is that clear? And now we have the phase at O, C, D, E, F, right? Now, how to obtain this phase? This is of the definition. Now, we see that in the equation y is equal to a sin omega t, that omega t represents phase at time t. That means we have phase at time t phi is equal to omega t, that is also equal to 2 pi by t into t. Here omega is constant, 2 pi by t is constant. Now the phase changes with time. Now we have y is equal to, right, this is also equal to a sin 2 pi by t into t. This term is representing phase here, omega t or 2 pi by t into t. Now at O, y is equal to a sin 2 pi by t into 0, that is equal to a sin 0. That means here the phase is 0. Now y is equal to a sin 2 pi by t into, at this position time taken is t by 4, that is equal to a sin pi by 2. So phase here it is pi by 2. Now at D, y is equal to a sin 2 pi by t into t by 2, that is equal to a sin pi. Now at E, y is equal to a sin 2 pi by t into 3t by 4, that is equal to a sin 3 pi by 2. At F, y is equal to a sin 2 pi by t into t, that is equal to sin 2 pi. So it is at O, C, D, E and F in the curve, right. See here, at O phase is equal to 0, at C phase equal to pi by 2, at D phase is equal to pi, at E phase is equal to 3 pi by 2 and at F phase is equal to 2 pi. Suppose what about phase phi is equal to 60 degree, right? When I say phase of a particle, so phi 1 at any instant of time is equal to 60 degree means the particle is in between O and C, somewhere here, the direction away from the mean position in positive direction. So when I say some phase phi 2 is equal to 120 degree, right, say here the phase position phi 1, so here it is phi 2, it is somewhere between C and D, right, but moving towards the mean position in positive direction. When I say phi 3 is equal to some 200 degree, it is somewhere here between D and E, but moving in, right, negative direction away from the mean position. When I say phi 3 is equal to some 300 degree, phi 4 is equal to some 400 degree, the particle is here. It is somewhere between E and F, but the direction of motion towards the mean position, right, in a negative direction. So all these phi 1, phi 2, phi 3, phi 4, right, are in 4 different directions. 2 in positive side and 2 in negative side. In positive side, away from the mean position towards the mean position. In negative side, away from the mean position towards the mean, right. So phase of a vibrating particle at any instant of time gives position of the particle and direction of motion of the particle at that instant of time. Why we need to, right, have a quantity called phase to describe the motion here? Because the path is retraced again and again at a regular interval of time about the mean position, right. Therefore, right, in one complete oscillation, right, the particle can have the same value of displacement at 4 instants of time. Here the displacement is same, but the direction of motion will be, right, different. Therefore, when we are locating an oscillating or vibrating particle at any instant of time, it is important to mention both position, that is displacement of the particle, as well as direction of motion of the particle at that instant of time. Then only we can exactly locate the position of the particle at any instant of time, right. Now this phase is a very important term when we are studying waves, where we continue this phase with another important thing, that is the phase difference. Here the phase difference between O and C is phase of C minus phase of O. Pi by 2 minus 0, that is equal to pi by 2. Here onwards we will express the phase in terms of, right, fraction of 2 pi, that is 0, pi by 2, pi, 3 pi by 2, 2 pi. Of course, it can also be expressed, right, in terms of fraction of time period, but it is more convenient to express the phase in terms of angle, because we have y is equal to a sin omega t, right. Now we can able to find the value of that sin omega t when we express omega t in terms of angle, right. Is it clear? Now that's all about this class, right. Now this is a very important class. Here we have the discussed, right, the graphical representation of simple harmonic motion, as well as very important the term, right, in the simple harmonic motion, that is phase, right. Okay, we will continue in the next class with more concepts. Thank you.